Hi Vijay. Hi everyone. Welcome to the session. Myself Dinesh. Very good evening. So I'm gonna take series of classes on Fourier transform, and this today's class is the first one. So for the next 6 days, I'll be taking many sessions on Fourier transform. I'll be mostly completing almost entire syllabus. Okay. So catch up with me for the next 7 days, same time, every day 1 hour. So I'll teach you Fourier transform in a wonderful manner. Okay. Hi Vijay Kumar. Good evening. Yeah, I hope the audio is clear. Thank you for confirming. So shall we start? Okay, fine. So let me say a few things here. So these are my subjects of expertise: communication systems and signals and systems. So I teach these two subjects for GATE and ECE exams. So if you wish to ask me any doubts based on these subjects, or if you wish to ask me any general questions, you can contact me in this group. So this is my Telegram group where uh, I interact with students. So any doubts on my subjects of expertise, you can ask me in this group. Okay, right. So what is the agenda of this today's session? So the agenda of today's session is, so we're going to talk about what is the condition for well-defined Fourier transform, and we're going to talk about the existence of Fourier transform for energy signal, power signal, and neither energy nor power signals. Out of these three signals, what signals have Fourier transform, what signals does not have? We're going to talk about that, and we're going to talk everything in detail. So these points are very important points, but many people miss these points generally. So yeah, so I'll summarize everything at the end of these two points discussion, and we'll do practice of some questions based on what we have discussed in today's session, and then I'll give you a few homework questions as well. Okay, how to get command on signals? So let me answer that question of Vijay first. If you want to get command on signals, the point is it's a very it looks like an easy subject, but it is not actually an easy subject. Okay, so you have to be very clear with the basics part. Like you should be able to easily add signals, differentiate signals. I'm not saying mathematically, graphically also you should be able to do it. So you should understand the minute details in signals very well. So if you can understand the basics of signals properly, then only you can understand the main topics well. Okay, it does not mean signals means it don't directly start with LTA systems or Fourier transform, Laplace transform. You have to go with first basics of signals. Okay, so how to shift a signal, how to plot a shifted signal, scaled signal. Okay, so you have to have a graphical imagination for every signal. So that is very important. So discrete case is, if you are able to learn continuous cases, discrete case is also similar understanding is there for discrete also. But the thing is, why we feel difficulty for discrete signals is because we are not used to them. So in most of our other subjects like control systems or communications or other subjects, we generally deal with continuous time signals, right? So we are comfortable with them, we generally see them, right? I mean, in our mathematical equations and all that. So since we are not dealing with discrete signals in many other subjects, so that's why we have sense of discomfort with discrete signals. But if you try to understand properly, discrete signals are more easy to deal with. Once you understand, you'll get that feeling that okay, discrete signals are more easy to deal with. Okay, so if you're feeling difficulty in anything, the only technique is to spend a little bit more time. Once you spend a little bit more time on the basics part of discrete signals, then I think discrete signals you will be comfortable with them. Okay, right. So first, let us go with mathematical formula. I think everybody knows this, but anyway, let me write it. Let me say if x of t is a signal, if x of t is a time domain signal, and for this signal we want to find the Fourier transform. Let me say the Fourier transform of this signal. Fourier transform of this signal. Let me denote it as capital X of omega. Since the Fourier transform is a function of frequency, it can be omega, or it can be a function of f also, because f and omega both are frequencies. Okay, so whatever is the letter that we use for time domain signal, the same letter, capital letter, we use for Fourier transform. That is the general notation. It does not mean that Fourier transform function should be always be denoted with capital letter. It's not like that. You can denote it with any letter, but that is the general notation that we use. If somebody gives you some g of omega with small letter as a function of frequency, is this not Fourier transform? Yes, this is also Fourier transform, but this is the standard format that we use. If somebody gives you in a question with a small letter function, that's fine, that's completely fine. That is also Fourier transform. Every concept is applicable for that function also. Okay, right. Okay, good. Fine. So let us write the formula for Fourier transform. X of omega or x of f, both of them, is equal to, the formula for this is equal to, very simple formula. I think many of you know this. X of t into e power minus j omega t dt, limits from minus infinity to plus infinity. See this one, you are integrating with respect to time, and after integration you are substituting the time with plus infinity and minus infinity, so t will vanish after integration, so it will be a function of only omega. So omega is nothing but 2 pi f, so if it is a function of omega, it is also a function of f. The result of this, you can represent it as x of f or x of omega, both ways it is fine. Right, wonderful. This is the formula for Fourier transform. Fine. Let's go ahead and learn a few more things, important things. So let us try to understand. These are very minute things, but very, very important things. So what is the meaning of well-defined Fourier transform? Sometimes we say Fourier transform is well-defined or not well-defined. Okay. So what is the meaning of it? So what is the meaning of it? Well-defined Fourier transform means a Fourier transform which has no undefined values, or which has only defined values. What do I mean by undefined values? It's like plus infinity, minus infinity. These are undefined values. Infinity, what does it mean? Sir, infinity is also a number. Yes, it is a number. It is so big that there is no defined number to represent it. So that's why we call infinity, plus or minus infinity, as undefined numbers. There is no proper number to define it. 10,000 crores, very big number, but it's properly defined as 10,000 crores. How much is the value? Exactly, it is defined. Infinity is so big a value that it is not properly defined. Okay, a Fourier transform, if it consists of infinite kind of amplitudes, if the Fourier transform consists of infinite kind of amplitudes, then we say it's not a well-defined Fourier transform. If a Fourier transform does not have these undefined values, then we say that it is a well-defined Fourier transform. I hope you are following. Is that okay? I guess everybody is understanding. It's very simple stuff. I hope you have understood what is the meaning of undefined values. Undefined values. Defined values means any number, any defined number other than plus or minus infinity. All the remaining numbers, all the other real numbers are defined numbers. Okay. Okay. Soumyak, what do you mean by that? Okay. Fine. We have understood what is well-defined Fourier transform. Well-defined Fourier transform means, I'll just get back to you once again. Well-defined Fourier transform, what is the meaning of it? It means x of omega, the Fourier transform of x of t has no plus or minus infinite values. It has no plus or minus infinite values. It has numbers, it has amplitudes other than plus or minus infinite. Okay, fine. Right. So what is the condition for well-defined Fourier transform? What is the condition? So all Fourier transforms need not be well-defined, right? All Fourier transforms need not be well-defined. So for a Fourier transform to be well-defined, what is the condition? Try to understand this. It is absolute integrability condition. So try to understand this. If x of t has a Fourier transform as x of omega, understand carefully. If x of t has a Fourier transform x of omega, and if you want this Fourier transform to be well-defined, which means no plus or minus infinite amplitudes. If you want this to happen, what is the condition on x of t? That is what is the question in this slide. What is the condition for well-defined Fourier transform on x of t so that x of omega will be well-defined? The condition here is, as they say, It's absolute integrability condition. Absolute integrability means take x of t, take absolute value of it, which means modulus of it, and integrability condition. What it means is if you integrate it with respect to time, because time is a variable here, if you integrate it, it should be finite. Absolute integrability means if you take the absolute value of the signal and integrate it, the result of this integration should be less than infinity. That is what is the meaning of absolute integrability. Absolute integrability condition is this. Less than infinity means it's a finite value. Okay, this value should be finite. Saying finite, if this value is finite, we can also say it as less than infinity. I hope everyone is following. Right. Now comes, now I'm just saying the same thing as a statement. A signal is absolutely integrable if the integration of modulus of the signal is a finite value. Whatever I've said here, I've written it as a statement. I hope everyone is following. Why does it happen? Let me explain this. Let me give you some commonsensical understanding of it. Okay. Let me write the Fourier transform formula here. X of omega is equal to integration of x of t into e power minus j omega t dt. Limits from minus infinity to plus infinity. This is the Fourier transform formula. Okay. Let us just analyze at omega equal to 0 what happens. Okay. It is x of t into e power 0. When you put omega equal to 0, it becomes e power 0, which is 1 dt, which means it is like integration of the signal. If x of t is not absolutely integrable, see this one. If x of t is not satisfying this condition, which means if you integrate x of t, it is turning out to be infinity. If x of t is not absolutely integrable, this implies integration of mod x of t dt is equal to infinity, right? If integration of mod x of t dt is infinity, it means if you integrate a signal x of t, instead of modulus, if you integrate the actual signal, that also might turn out to be infinity, right? That also might turn out to be infinity, correct? It might turn out to be plus infinity, or it might turn out to be minus infinity also. I hope you're following. Correct? So which means x of omega, the Fourier transform at one frequency, is it having infinite amplitudes? Is it having infinite amplitudes? If the signal is not absolutely integrable, its area is infinity. If its area is infinity, the Fourier transform at one frequency omega equal to 0 is definitely an infinite amplitude. The amplitude of the Fourier transform at omega equal to 0 is infinity. Correct? Which means at least one frequency, if the Fourier transform is having undefined values like this, infinite values, at one frequency at least, if you are having undefined values, infinite values, then we can say the Fourier transform is not well defined. Correct or not? See, that I am showing you the opposite case. If x of t is not absolutely integrable, which means if this integration is equal to infinity, then x of omega equal to 0 is turning out to be infinity, which means the Fourier transform is not well defined. Not only at omega equal to 0, you might get infinite values at some other frequencies also, because if you put some other omega values, this result of this integration might, I'm not saying always, for all frequencies it will happen, but for some other frequencies also, this integration result might turn out to be infinity, because area of x of t is infinity. If x of t area is infinity, then x of t is multiplied with some signal and then integrated. That also might result in infinite values. Correct? But if x of t area is finite, if x of t is area is finite, if you multiply that signal with some other signal, and then integrate, the result is the result will be a finite value, because this is absolutely integrable. Hence, if you multiply with some other signal and then integrate, the result will turn out to be a finite values. For all values of omega, it will be finite. I'm trying to explain the same condition that I've discussed in this slide with an example. Okay. I hope you've understood now why we get a well-defined Fourier transform. Well-defined Fourier transform means the Fourier transform without a plus or minus infinite values. Okay, why we get a well-defined Fourier transform for an absolutely integrable signal. Okay, so because I have taken the negative case, if x of t is not absolutely integrable, I have shown that it is taking infinite values, undefined values. So the opposite of it is, if it is absolutely integrable, then definitely x of omega will be well defined. Okay, I hope it is clear. Right, I'm moving on to the next slide. Let's move on to the next point. Fourier transform formula be applied for all signals. Can we apply? Can you say yes or no? I'm asking you a question here. Can Fourier transform formula can be applied for all signals? All types of signals. Is it possible? Sir, there is a formula. Who is stopping me from substituting? Yes, nobody is stopping you from substituting. But applying that formula for all signals is not right. It is not right. We can't apply the Fourier transform formula for all signals. You may say that, sir, formula is there, I'll apply. No, that's not good. If you apply also, you'll get some vague answer. Okay. Right. Let me explain. The answer is no. Can Fourier transform formula be applied for all signals? No, we can't apply. We can apply only for certain signals. So I'll tell you for what kind of signals you can apply Fourier transform formula. Okay. Right. Fourier transform formula can be applied for signals which have a well-defined Fourier transform. Yes. Try to understand this. What signals have well-defined Fourier transform? Signals which have well-defined Fourier transform are absolutely integrable signals. Which means Fourier transform formula can be applied for what signals? Absolutely integrable signals. Only for absolutely integrable signals. Only for absolutely integrable signals we can apply the formula for Fourier transform. The signals for which we can apply Fourier transform formula to get the Fourier transform is absolutely integrable signals. Sir, other than absolutely integrable signals, the remaining signals, don't they have Fourier transform? Some of the signals have Fourier transform. Though we can't apply the formula, they have a Fourier transform, and there is a way to find it. I'll tell you that in the next slide. Understand carefully. We can't apply Fourier transform formula for all signals. We can apply it only for absolutely integrable signals. Okay. Right. Let us move on to the next slide. Does Fourier transform exist for non-absolutely integrable signals? Signals which are not absolutely integrable signals. Signals which are not absolutely integrable. What do I mean by non-absolutely integrable signals? If we take modulus of the signal and integrate it from minus infinity to plus infinity, that result will turn out to be infinity. So these kind of signals we call them as not absolutely integrable signals or non-absolutely integrable signals. For these kind of signals, does Fourier transform exist or not? Does it exist? Yes, no? Anyone? Does Fourier transform exist for non-absolutely integrable signals? I'm not asking does a well-defined Fourier transform exist. My question is not well-defined about well-defined Fourier transform. Well-defined Fourier transform exists only for absolutely integrable signals. For non-absolutely integrable signals, definitely well-defined Fourier transform does not exist. But I'm not talking about well-defined Fourier transform, just Fourier transform. Well-defined Fourier transform means a Fourier transform without plus or minus infinite values. I'm not talking about well-defined Fourier transform, just Fourier transform. Fourier transform means it can be with infinite plus or minus infinite values also. When I say Fourier transform without well-defined word, it means it is acceptable to have plus or minus infinite values. Okay, right. Let's see. Let's try to understand carefully. Generally, absolutely integrable signals are energy signals. I hope everybody understands the meaning of energy signals. If energy is infinity, if you take x of t signal, you can find the energy by taking the modulus, square it and integrate it. Okay, if energy is finite, this is the definition of energy being finite. Then if energy is finite, x of t is an energy signal, right? See this one, absolute integrability condition. Here I have written this here. Absolute integrability condition and energy signal condition, both are looking similar. Not exactly same, but they are looking similar. If you find the area of a signal and if it is finite, obviously if you square it and find the area, then also it will be finite, no? Correct or not? Right. Absolute integrability condition and energy signal condition, both are looking similar. For most of the signals, for signals which are absolutely integrable, generally, that's why I said general, not always, but most of the cases, absolutely integrable signals are generally energy signals, and vice versa also. Which means energy signal. If you see a signal and somebody says that it is an energy signal, Definitely, if you find absolute integrability of it, it will be absolutely integrable. Understand carefully. These are very, very important stuff. Right. I've told you the exceptions also here. Impulse function. I'm talking about only continuous time case because Fourier transform is dealing with continuous time Fourier transform. We're dealing with continuous time signals. Okay. So continuous time impulse, which is del of t, and sinc function, sinc of at, this kind of signal. These are known exceptions for above statement. So see this one, continuous time impulse function is absolutely integrable, correct? Because area of unit impulse is 1. Area of any impulse, any continuous time impulse is finite only, right? So continuous time impulse function is definitely absolutely integrable because its area is finite. But it is not an energy signal. You might have learned this, right? Continuous time impulse function is not an energy signal. It's a neither energy nor power signal. Next, continuous time sinc function is not absolutely integrable, but it is an energy signal. See this one? There are only two exceptions. Only two exceptions that we know of. There might be some other functions also which we are not aware or which we don't generally use. These functions we generally use in our in all subjects, right? So among the functions that we use in our subjects, these are the two exceptions which violate the first statement. Okay, all absolutely integrable signals are energy signals, and all energy signals are absolutely integrable except two signals, and they are continuous time impulse. It is absolutely integrable, but it is not energy signal. Continuous time sinc function, it is not absolutely integrable, but it is an energy signal. These are two exceptions. Let's leave these exceptions because we know the exceptions also. Let's leave these exceptions. But for other signals, if you know that it is an energy signal, it is an absolutely integrable signal. Correct? Right. So, as we discussed, energy signals are generally, most 99% of them, energy signals are all absolutely integrable, correct? And similarly, absolutely integrable signals are generally energy signals. We have seen the exceptions in the previous slide. When I say energy signals are absolutely integrable, I am not taking those two signals into consideration. Okay. So absolutely integrable signals are energy signals. So when I say non-absolutely integrable signals, what are the two signals that are remaining? We're talking about energy signal, power signal classification. Okay. So apart from energy signal, there are two other signals: power signals and neither energy nor power signals. So if you observe the classification, energy signals, power signals, neither energy nor power signals. These are the three classifications that we have. Any signal can be classified into one of these three. Okay. So we have discussed that absolutely integrable signals are energy signals, right? We have discussed that. So what are the remaining two signals that are not absolutely integrable? They are power signals and neither energy nor power signals. Okay. So the question is, does Fourier transform exist for non-absolutely integrable signals? Which means I'm talking about, does Fourier transform exist for power signals and neither energy nor power signals? I'm talking about these two signals. Because Fourier transform definitely exists for absolutely integrable signals, and it is also well defined. But the question is not about absolutely integrable signals. The question is about non-absolutely integrable signals, which are power signals and neither energy nor power signals. Okay, understand carefully. Of these two non-absolutely integrable signals, power signals have Fourier transform. Mind this: power signals have a Fourier transform. All power signals, they are not absolutely integrable. Power signals are not absolutely integrable. So that's why they will not have a well-defined Fourier transform, but they have a Fourier transform. Power signals, they have a Fourier transform, but it is not well defined because they are not absolutely integrable. So let me write that also. Power signals, are they absolutely integrable? Remember, power signals, any periodic signal, the sine signal, cos signal, u of t, a constant function, these are all power signals. These power signals, okay, they are not absolutely integrable because their area is infinity. Power signals are not absolutely integrable. Hence, they don't have a well-defined Fourier transform. Mind this: having a Fourier transform is different from well-defined Fourier transform. They don't have well-defined Fourier transforms, but they have a Fourier transform, which means whatever is the Fourier transform of power signals, they might have infinite kind of values, undefined values. They have a Fourier transform. U of t has a Fourier transform. You might have known the formula. Cos omega naught t has a Fourier transform. Yes, they have a Fourier transform, but their Fourier transform consists of infinite kind of amplitudes. For example, let's take something. 1. What is the Fourier transform of 1? Fourier transform of 1, constant 1, is 2 pi into del of omega. This is the Fourier transform. Del of omega means what is the height of it? What is the height of it? Del of omega height is infinity, no? Del of omega height is infinity, right? So is the Fourier transform consisting of infinite amplitudes, undefined values, impulse, continuous impulse, height is infinity, which is undefined. I hope now you are understanding. Power signal, one is constant signal is a power signal. It has a Fourier transform, but is it well defined? It has a Fourier transform, but not well defined because it is having infinite kind of amplitudes, because impulse height is infinite. Okay. Omkar, definitely I'll clear your doubts. You can go ahead and ask once the session is complete. If it is within the topic, I'll clear it now itself. Otherwise, I'll clear it at the end of the session. Okay, right. So because power signals are not absolutely integrable, they don't have a well-defined Fourier transform. Correct. That is what I've written here. I've given you an example also. If you want, you can write for other signal also. Cos omega naught t Fourier transform. If you find, if you remember, you can write it. It is pi into del of omega minus omega naught plus del of omega plus omega naught. Yes, this power signal cos omega naught t is a power signal. It has a Fourier transform. It has a Fourier transform. Yes, it has a Fourier transform. Fourier transform exists for power signals, but is it well defined? No, because it has impulses. Impulses means whose impulses will have a height of infinity. Undefined height, undefined amplitudes are there. So this is a Fourier transform, but it is not well defined. Well defined means only defined value should be there, no plus or minus infinite values. Because this is having infinite values, that's why we are calling it as not well defined. Because if only well defined numbers, finite numbers are there, we call it as well defined. If undefined numbers are there, we call it as not well defined. Right. So Fourier transform power signals can't be found using Fourier transform formula. It should be found using properties of Fourier transform. Mind this. If you remember previous slides, I've told you that we can use Fourier transform formula only for absolutely integrable signals, right? We can use Fourier transform formula only for absolutely integrable signals. As we have discussed, power signals are not absolutely integrable. If they are not absolutely integrable, we can't apply Fourier transform formula. Sir, if we can't apply Fourier transform formula, how can we find it? Yes, there are other ways to find it. Using properties. There are a lot of properties for Fourier transform. Using those properties, we can find Fourier transform of all power signals. Okay. So how we do that? We'll discuss that in the next classes. When we discuss about properties, we'll discuss about how to find Fourier transform of power signals. Okay. That is the understanding. How about neither energy nor power signals? Power signals have a Fourier transform but not well defined, and we have to find the Fourier transform by using, but we can't use Fourier transform formula, mathematical formula to find Fourier transform. We have to use alternate procedures to find Fourier transform power signals. For energy signals, they're absolutely integrable. We can find Fourier transform using Fourier transform formula itself, and the Fourier transform will be well defined. Right. For neither energy nor power signals, Fourier transform does not exist at all. Correct. I am having the formula. Na? I will substitute that formula for neither energy nor power signal. So who is stopping you? Nobody is stopping you. Even if you substitute, you get some answer. But according to the definition, they don't exist. Na? When they don't exist, if you find something and you get some answer, and if you are telling me that answer, why are you telling me that answer which does not exist? There is no answer for it. When somebody asks me Fourier transform of neither energy nor power signal, it does not exist. Then what is the point of applying the formula and finding something? Okay, sure, Harshit. I'll get back to you. Okay, just wait for a minute. I'll clear all those doubts. Just a few minutes. This session is almost done. Once that is done, I'll clear your doubts. Okay. So Fourier transform does not exist for neither energy nor power signals. Neither energy nor power signals means kind of exponential signals, e power minus plus 3t into u of t, this kind of signal. Okay. Or e power minus 3t into u of minus t. This is also an exponentially increasing signal on the negative time. So these signals, they look like this. These kind of signals are neither engine nor power signal. There are a lot of other examples also. For these signals, don't apply the Fourier transform formula. Don't try anything to find the Fourier transform because it does not exist. When somebody gives you this kind of signal, if you can identify that it is neither engine nor power signal, if he is asking for Fourier transform, tell him that it does not exist. You don't need to ask because it does not exist. Right? What is the summary? So let me summarize what we have discussed till now. The condition for a well-defined Fourier transform is the absolute integrability condition. If you want well-defined Fourier transform, it exists only for time domain signals which are absolutely integrable. For energy signals, Fourier transform exists. It is well-defined, and also one more thing, you can find Fourier transform using the formula that we have discussed in the first slide, using Fourier transform formula. Power signals, Fourier transform exists, and it is not well defined because power signals are not absolutely integrable. Only for absolutely integrable signals, Fourier transform is well defined. So power signals, Fourier transform is not well defined, but it exists, and we can't find the Fourier transform. Fourier transform we can't find using Fourier transform formula, but we have to find Fourier transform using properties. Using properties of Fourier transform, we can find it. Not by using formula, because formula is not applicable to this. Okay, how we find the Fourier transform power signals we'll discuss in the next session. Okay, for neither engine nor power signals, don't even think of finding Fourier transform because it does not exist. Okay. Okay, I think Harshit is asking some question which is related to this. What is the difference between trigonometric Fourier series and exponential Fourier series? Yeah, it's very simple relation, right? Trigonometric Fourier series means it involves cos omega naught t and sin omega naught t, and there is a relation between cos omega naught t and sin omega naught t. Sorry, e power j omega naught t. If you substitute in place of cos and sin, this relation, the trigonometric Fourier series gets converted to exponential Fourier series. As simple as that. They are very much related. They are very much related. So I'll tell you something. One second. E power j omega naught t. What is the Fourier transform of this one? If you remember Fourier transform, then it will be easy for me to make you understand. Okay. So e power j omega naught t Fourier transform is del of f minus f naught, or 2 pi into del of omega minus omega naught. So what is the frequency? If you plot the Fourier transform of this one, there is a frequency only at f naught. Okay, only frequency at f naught with an area of 1 unit. Whereas cos omega naught t Fourier transform is del of f minus f naught plus del of f plus f naught divided by 2. It means if you plot the Fourier transform of cos omega naught t, it represents two impulses at f naught and minus f naught. It represents two impulses at f naught and minus f naught. See the difference? Cos omega naught t consists of two frequencies, actually one frequency, only one positive frequency and the symmetric negative frequency, whereas e power j omega naught t is having only one frequency. See, cos omega naught t is a real signal, whereas e power j omega naught t is a complex signal. For a signal to be real, you might have learned this property. For all real signals, Fourier transform will be conjugate even symmetric. Okay, and magnitude spectrum will be even symmetric. This is a complex signal. For this, only positive frequency exists, but no negative frequency, because there is no symmetry condition for complex signals. Whereas this is a real signal for which Fourier transform should be having some symmetry. Okay, so the difference between trigonometric Fourier series and exponential Fourier series is they represent the same information but in a slightly different format. In trigonometric Fourier series, we try to represent the Fourier series using real signals. Cos omega naught t, sin omega naught t are real signals. They give only real values. Whereas in exponential Fourier series, we represent the same representation. We do it with complex signals, or we call them as complex sinusoidal signals. E power j omega naught t, we call it as complex sinusoidal signals. Okay. I'll come to that, Sharma. Harshit, I'll come back to your question. Picture that we get after multiplying cos omega naught t with rectangle of t by t asked to me in IIT Madras. Okay, very good. Let me answer that. Okay, let me answer Harshit's question. Harshit is asking a question. A question was being asked in IIT Madras. It seems it's a very simple question, Harshit. Cos omega naught t, how does it look like? It looks like this. If they have given exact cos signal, I think they have given, right? Yeah, you have a cos omega naught t, right? Okay. Excuse me for I'm not good at drawing. So rectangle. Okay. So this is cos omega naught t. Okay. So omega naught is equal to, let us write it as 2 pi by t. Harshit is saying that rectangle of t by t. Rectangle of t by t means I'm assuming that this width of the rectangle and this time period both are same. I'm assuming that. Okay. If they are different, you can the analysis will be different. Let me assume it is same and do it. Okay. So then it will be, if the time period is t, then it will be from minus t by 2 to plus t by 2. Correct. And this will be 3t by 2. Is that okay? 1 second, my mistake. It's not minus t by 2 to plus t by 2 because total period is t. No? So this is minus t by 4. This is plus t by 4. This is t by 2. And this is 3t by 4. See this one? From here, minus t by 4 to plus 3t by 4. To total time period is t units. Or from here, if you start, one cycle completes here. So if this is 0, this is t. Yeah. Now rectangle of t by t. Let me plot this also. This is minus t by 2. So if you plot that rectangle of t by t, minus t by 2 to plus t by 2. I think you got the answer now, Harshit. So what do you get? You get this waveform. You can copy that as it is. And till t by 2 you can copy. And after that, 0 multiplied with anything is 0. So you can stop at this place, something like this. Similarly here also. Minus t by 2 to plus t by 2. Is that okay? They told time period is same. Okay, they're asking about frequency domain. Okay, good. So they're talking about frequency domain. Okay. Okay, that's a good question. So rectangle of t by t Fourier transform is, think of omega naught into t divided by 2 pi, correct? Now, if you multiply that, this is a rectangle of t by t multiplied with cos omega naught t. Fourier transform of this is, rectangle Fourier transform is sinc. When you multiply with cos, what happens on the other side? Whatever is the function that gets shifted towards right side by omega naught and left side by omega naught. Or if you remember, there is a property for multiplication with cos omega naught t. If you want, I'll write the property also here. X of t into cos omega naught t. Any signal, if you multiply with cos omega naught t, Fourier transform, what happens to the Fourier transform? My mistake. I think it's hiding it, right? Yeah, Fourier transform of this is x of omega minus omega naught plus x of omega plus omega naught divided. When a signal in time domain is multiplied with cos signal or sine signal, in frequency domain what happens? Shifting happens towards right side by whatever is the frequency in cos. Signal shifting happens towards right side by that much frequency and left side also by that much frequency. Amplitude gets reduced by 2. That's fine. Sinc or sampling both are fine. Na? So if you write it as sampling function, it is sampling of omega naught t by 2. Is that okay? Now it will be sinc of, if you want, I'll write it as sampling of only. Sampling of 1 second. It's not omega, no? Because it's a function of frequency. It should be omega. Okay. So it is omega minus omega naught into t divided by 2 plus sampling of omega plus omega naught into t divided by 2, whole thing divided by 2. This is the answer. If required, you can do some extra simplification also if they are expected. So professors, they get angry just to test your confidence. So that is the answer. Yeah, fine. So next I'll go to the next question. Some time. Sharma, CSE at SRM or CSE at KIIT? Where is KIIT? I know of SRM, but the KIIT, SRM is definitely good. KIIT, I'm not aware, Aditya. Uh, you can inquire others. Okay, KIIT, I'm not aware. So it's SRM, I'm sure it is good. Okay, so better consult someone, yeah, about KIIT and then take a decision. Feature transform and inverse feature transform. What is the difference from Fourier? Feature transform. I'm not sure of feature transform. Not come across that kind of transform. I'll let me search for it. Figure of what? The sampling function. Okay, okay, that's fine. We can do it. No? So simple sampling function means it looks something like this. Let me draw only one cycle, okay, just to avoid confusion. So if you plot this, it is like a sampling function here and a sampling function here with side loops will be there at omega naught and minus omega. If you want, you can draw the side loops also. Similarly on this side. Okay. Fine. I hope it is clear. Right. So finally, anyway, let me complete this session by asking some questions. X of t is equal to e power minus 2t into u of t. Can anyone tell me if this Fourier transform exists, if the Fourier transform for this signal exists or not, and if it is well defined or not? Can you tell me? Anyone? So this is an exponentially decreasing signals. Just imagine this graph of it. It's like exponentially decreasing. If it exponentially decreasing, its area is finite. So this signal, this is absolutely integrable. If it is absolutely integrable, Fourier transform exists, and it is also well defined. For all absolutely integrable signals, Fourier transform is well defined. Next one, you can observe that this is an exponentially increasing signals. So any signal which takes infinite amplitude at any one point of time, those are all neither energy nor power signals. For neither energy nor power signals, Fourier transform does not exist. Okay, right. Next, how about some kind of periodic signal, something like a u of t kind of signal? So this is a power signal, right? This is a power signal, but it is not absolutely integrable. Power signals are definitely not absolutely integrable. So Fourier transform exists, but not well defined. That means it will have infinite kind of values. Not at all frequencies, but at some frequencies it will have undefined values. Is that okay? Right. I don't know what he's angry about. He might be frustrated with something else, and his mindset is not right at that point of time. So you're unlucky to enter at that point of time, maybe, or he's basically an angry guy, maybe. Okay. So their reaction does not, their reaction is bad does not mean that you are not performing well, right? They are not in a good mood, maybe. Okay, okay, sure. Kiran, you're asking something. H of t is equal to, is it del dash? Okay, del dash of t minus 4. I'm assuming it is del dash of t minus 4. Correct me if that is not the question. Del dash of t minus 4 means it's a doublet. It's a doublet. So impulse is absolutely integrable. Del of t is absolutely integrable. Yes, is because its area is finite. But del dash of t is not absolutely integrable because impulse is something like this. Its area, its height is infinity. Its height is infinity, but its area is unity. The area of impulse, the area of impulse is 1. Whereas a doublet means it is something like this. An impulse at 0 minus, an impulse, negative impulse at 0 plus. There are two impulses, and the area of this positive impulse is infinity, and the area of this negative impulse is minus infinity. Okay, if you take the absolute integrability of it, if you apply modulus, both impulses will become positive, and you find the area, the amplitude is infinity, and the area is also infinity. Whatever is written beside the impulse, that is the area, not the amplitude. Mind this. The amplitude of impulse is always infinity. What is written beside it is always the area of it. For a doublet, the area is infinity. So del dash means it's a doublet. Del dash of t minus 4 means it's shifted to 4. The same signal shifted to 4. So since this is not absolutely integrable, it is not stable. Stability is nothing. Stability condition is absolutely integrable condition. For systems, if the impulse response is given, if the impulse response is absolutely integrable, then it is a stable system. Okay, and causality is very simple, no? So this is existing in positive time, and hence, if impulse response is causal, as a signal, if it is causal, then system as a system also it will be causal. So it is not stable, it is not stable, and it is causal. See, Kiran, we are not applying integrability; we are applying absolute integrability. If you apply modulus to this signal, this negative impulse will become positive impulse. I hope you're following. It's not integrability. It's not just finding the area of the signal. Find the area of modulus applied signal. Apply modulus to this. The negative becomes positive. Then area will be infinity. I guess you're following. Right. Homework. Let me give you a few questions as homework. X of t is equal to e power minus 3t plus e power 4t. This is the first homework question I'm asking you. Fourier transform exists or not for following sequence. Just it exists or not. Yes, no kind of question. You can comment the answers in the comment section, not in the live chat, in the comment section if you are able to solve it. So I'll check the comments, and if they are correct, I'll give you the answers for these questions in tomorrow's session at the starting of the session. Next one. Okay, so I've given you 3 homework questions. You can solve it after the session, and you can comment the answers 1, 2, 3. Yes, no. Fourier transform exists. Yes, no. Just comment for 1, 2, 3 questions in the comment section. I'll check your answers and update you if they are correct or not. Point ohms, I'm not aware of Fourier transform. That is a little advanced concept. So I'm an expert only in the syllabus that is corresponding to GATE. Okay. So that is a little advanced transform. So I'm not aware of it. If you are interested, you can browse through internet and you can learn from it. Okay, fine then. So I'm stopping at this place. So we'll meet again in tomorrow's session. Okay, take care, good night. We'll see you tomorrow same time. We'll talk about some other concept on Fourier transform. In the next 6 classes I'll be covering most of the Fourier transforms, most of the properties, most of the concepts based on Fourier transform will be covered in the next 6 classes. Okay, so if you wish to learn Fourier transform, you can follow these classes.